Hello and welcome to this video about superconductors and how magnetic field lines behave in their presence. Before watching this video, it might be a good idea to watch my video on conductors in an electric field, which is simpler and is good to develop an understanding of how to calculate the charge distribution in such a material using matrices, and then to use this charge distribution to draw electric or magnetic field lines. Superconductors are a bit more complicated since they use point dipoles, which generate magnetic fields that are difficult to calculate and go in all sorts of directions. It might be a good idea to watch my video on point dipoles as well. Point dipoles obey the inverse cube law, so their influence dies off more quickly than that for monopole charges, which obey the inverse square law. This could explain why the magnetic field gets deflected only when it is very close to the superconductor, and looks very different to how it looks in textbooks. We'll use a magnetic monopole to induce dipoles in the superconductor, and then calculate the magnetic field as it radiates away from this monopole. Magnetic monopoles are very hard to create, even if they can exist, but it is easy to create something that looks and behaves like one, even if it isn't one. The lines of magnetic field aren't beautiful like they are for the conductor in an electric field. We'll use a matrix to find the dipole distribution in this superconductor, and then use them to calculate the corresponding magnetic field. So now to use some geometry to make some derivations. Point A will be our observation point, and P will be our point dipole. We'll calculate the magnetic field at A due to P. We'll firstly calculate the distance between these 2 points, and d cubed will be the quantity that we'll use most often. After zooming in, we'll need to find the angle beta. This is necessary to calculate the magnetic field at A due to P. To do this, we'll find the vertical and horizontal components of the distance between them. We'll also index these quantities. A will be indexed with I and P with J. So the next step is to get the angle gamma from these 2 distances, which is usually done using the inverse tangent function, but there's a clever function used in JavaScript that can get the angle from these 2 sides of a right-angled triangle immediately, and not having to do anything else, like check if distance x is negative. And so from the diagram we can see that this formula for beta is true. So now the magnetic field at point A caused by the dipole at point B is given by this compact equation in terms of the unit vectors that describe the inclination of this dipole, I' and J'. You can see that it has a very complicated way of changing its direction. So this is what the unit vectors are in terms of the absolute unit vectors I and J. We'll substitute these equations into the top equation to give us this equation. And simplifying this equation gives us the magnetic field in terms of I and J. Since surface dipoles that were normal to the surface didn't produce good curvature for the lines of magnetic field, I needed to make the dipoles able to have an angle different to that of the surface normal. I did this by having another dipole at the same location, but perpendicular to it. Since dipoles are linear, they can be added together to make a dipole that can have any angle. This required having twice as many positions to check the magnetic field for. So here are the alternative calculations for it. The new value for beta is given by this formula according to the geometry. And we'll substitute this new value for beta into this equation for the magnetic field. And because this angle is tilted at right angles to theta, we'll make this substitution for all the occurrences of theta found in the next two equations, so that now they look like this. I want to express this magnetic field in terms of r and o unit vectors, that is, unit vectors that are perpendicular to and tangential to the surface of the material, and I'll do it by multiplying these above values of b by the cosine and sines of the middle angle alpha. I want to do this so that I can express a dipole in terms of the unit normal and unit tangent of the surface of the superconductor, which seems to be the best way of describing them. I won't substitute the top equations into these equations because I'm writing a computer program to find and solve for them, and won't really need to. It'll only make these already messy equations even more messy. The next step is to get an expression for the sum of all the magnetic fields caused by all of the magnetic dipoles on the surface of this superconductor, which can be expressed like this. And then it can be expressed like this. These vectors in absolute value brackets already point in these directions, but I wanted to write them out like this to more emphasize the directions that they are in. The next step is to include the magnetic point charge in this calculation, which induces the dipoles in this superconductor. It needs to be non-zero, otherwise all of the dipoles will equal zero. So this is what the magnetic field of this magnetic charge is. If you'd like to see how to get it more precisely, I'd refer you to my video on a conductor in an electric field. And this is what the radial component of this magnetic field is. The total magnetic field at point A must be tangential to the surface at A, and only have a component in the direction O, going anti-clockwise around the circle, and thus having no component in the unit r direction, and that is why this expression is set to be zero. So evaluating these dot products gives us this, and substituting these more accurate expressions in gives us this. The first is the sum of all the magnetic fields caused by all of the dipoles on the surface of this material, and the second is the magnetic field caused by the external magnetic charge. And after scrolling these equations up, I can fit another equation in, which expresses this sum in dot notation, and I can subtract the magnetic field caused by the external charge from both sides. I'll just write it up here again for a short amount of time to let it sink in. Then I can substitute these expressions in for the values of b, so b isn't written here. And I can divide both sides by k, which doesn't need to be known for these purposes anyway. I can then factorize this common term, b divided by d cubed, outside of these brackets for each term. I'll just define the function f to be this, so as to simplify the mathematics. And I'll define g to be this, and so this long equation simplifies to become this. And this equation can be expressed as this vector equation. And I'll just write it up again here. And if I have a large amount of positions on the surface of the superconductor that have zero magnetic field in the direction r, and if the number of these positions is equal to twice the number of dipoles, I can create this matrix equation and solve for p, thus finding the dipole moment of each dipole. The dipoles are in two directions, r and o, so this causes two surface positions of magnetic field to be found for each dipole. And so this is what the magnetic field looks like on the conductor, facing a direction that circles the conductor and are tangential to the surface. In this case, I put these positions a bit above the superconductor. And here is another picture of what these surface magnetic fields would look like. It must be noted that due to the nature of dipoles compared to monopoles, it doesn't make the accuracy any better by making more dipoles for one value of dipole moment, the way it did in the electric field problem. But it worked well for a small number of dipoles, like 11, and having only one value of dipole for each value of dipole moment. This is what the surface dipoles look like, the location of them being at the tail of the arrow. Notice that they aren't normal to the surface of the superconductor. I couldn't get the calculations to work for them if they were, so I had to add a tangential component to them. I did some ray tracing for them with a single ray of magnetic field. Notice that they come very close to the superconductor before they deflect and travel around it. In this case, it changes sides asymmetrically, possibly caused by there being only 11 dipoles. After it has been deflected, it doesn't travel back around the conductor to travel in the path it would have taken if the superconductor wasn't there, which it would in the real world. I'd just like to go through the code that I used to create the matrix used to find the values of the dipole moments in the superconducting material. We firstly have to have the number of dipole positions that would contain two dipole values each, because they are two-dimensional vectors. The number of positions where the magnetic field is measured on the surface is double this value, and is called the number of nulls. We then have to calculate the positions of all these surface dipole positions, and insert them into the surface dipole structured type. Each position has two values of dipole moment that are set to 0 for now, before they eventually get calculated. I've set them to be a little bit beneath the surface to give me a better picture of the magnetic field lines. Next, the positions of all the locations used to measure the magnetic field are calculated. The normal component is to be measured to be 0 so as to give tangential magnetic field lines on the surface of the superconductor as shown, and are to be slightly displaced from the dipoles. I've set them to be slightly above the surface of this superconductor. Now for the creation of the matrix, and it will be an augmented matrix, with the number of columns being equal to the number of rows plus 1. I've initiated 2 loops, because a matrix is a two-dimensional structure. I've calculated all of the distances here. dr3 is the variable that we'll be using here. So I've calculated the value of beta, and a final number that will be multiplied by the dipole moment to give me the magnetic field. So I'll just write it up the top of the screen here to see where we're up to. And we'll do a similar thing for the component of the dipole moment that is tangential to the surface for each dipole location. We'll insert these values into the matrix. Now to calculate the distances between the surface nulls and the external magnetic charge. Then we'll calculate values from these distances and external magnetic charge and insert them into the last column of the matrix. We'll then use a function to solve for this matrix, usually called reduce, or it can be a specially written function somewhere in your own code. This will cause the last column to contain the values for all of the dipole moments that we want. We'll then use a final loop to insert them into the dipole structured variable. So this is a list of the values of these dipoles in these directions. I wasn't successful at finding a function for them because they were too erratic. So thank you for watching this video, and I wish you all the best in your quest to study this sort of electromagnetism.